Subscribe to the channel so you don't miss out on any of these videos. The quest to unravel the secrets of the cosmos has led scientists down countless winding paths, each one promising a new glimpse into the hidden realms of our universe. Among the most fascinating mysteries we seek to understand are exoplanets, planets beyond our solar system, orbiting stars light years away. For centuries, humanity wondered if such distant worlds existed. Today, we not only know they do but are continuously refining techniques to detect them with greater precision. One groundbreaking method, gravitational microlensing, has emerged as a powerful tool for detecting these elusive worlds, especially those hidden from other detection methods. This captivating phenomenon, born from the warped fabric of space-time itself, is reshaping our understanding of planetary science and bringing us closer than ever to identifying other potentially habitable worlds. Gravitational microlensing is an elegant manifestation of Einstein's theory of general relativity, which proposed that massive objects could bend the space-time around them, thus altering the path of light. When a massive object, such as a star, passes between a distant star and an observer on Earth, the gravitational field of the nearer star acts as a lens, bending and magnifying the light of the more distant star. This effect is known as gravitational lensing, and when applied on a smaller scale to observe the influence of a planet on a star, it is referred to as microlensing. Unlike other planet hunting methods, which typically rely on detecting direct starlight or slight wobbles in a star's position, microlensing enables the discovery of planets by amplifying the light of stars lying far beyond. The beauty of gravitational microlensing lies in its ability to detect exoplanets that are otherwise invisible to other techniques. Traditional methods such as the transit method, which identifies planets based on the dip in a star's light as a planet crosses its path, require a direct line of sight. Similarly, the radial velocity method detects planets by observing the wobble of a star caused by a planet's gravitational pull, which is only observable for relatively close systems. But microlensing can detect planets even if they do not align in any particular way, as long as the gravitational lensing event occurs. Furthermore, microlensing does not depend on the brightness of the host star, allowing for the detection of planets around faint or even undetectable stars. This versatility has led to the discovery of some of the most intriguing and distant exoplanets known today, offering insights into the diversity and complexity of planetary systems throughout the galaxy. Microlensing events are rare and fleeting, as they require the near-perfect alignment of a background star, a lensing star, and the observer on Earth. However, when such an event occurs, it provides a wealth of information. As the lensing star, and any accompanying planet, passes in front of the background star, the planet's gravitational field adds a subtle but detectable distortion to the light curve produced by the lensing star. By analyzing these distortions, astronomers can estimate the planet's mass, distance from its host star, and sometimes even the presence of multiple planets in the same system. This precision has enabled the discovery of planets located in regions of space that were previously beyond our reach, revealing worlds that might otherwise have remained hidden. One of the most famous microlensing discoveries occurred in 2005 when scientists announced the detection of an exoplanet orbiting a star approximately 20,000 light-years away in the constellation Sagittarius. The planet, designated OGLE 2005 BLG 390LB, was detected by the Optical Gravitational Lensing Experiment, OGLE, and the Microlensing Observations in Astrophysics, MOA, collaboration. It was the most distant planet ever discovered through microlensing at the time, and is thought to be a super-Earth, with a mass about 5 times that of Earth. Located in the cold, outer regions of its solar system, OGLE 2005 BLG 390LB likely experiences frigid temperatures, with a surface covered in frozen water and perhaps an atmosphere of nitrogen. This discovery demonstrated that microlensing could unveil planets in environments vastly different from those in our own solar system, expanding our understanding of planetary formation and diversity. Since then, microlensing has uncovered numerous other exoplanets, each contributing to the growing catalog of worlds beyond our solar system. The technique has proven particularly effective in finding planets in the Milky Way's galactic bulge, a dense, star-filled region where traditional detection methods often struggle. For instance, in 2013, a team of astronomers discovered MOE 2011 BLG262LB, an exoplanet that might orbit either a faint star or a rogue planet, a planet not bound to any star. This discovery hinted at the possibility that rogue planets, free-floating and drifting through the galaxy, might be more common than previously thought. Such findings underscore the potential of microlensing not only to locate planets around stars but also to reveal worlds that wander alone, unattached to any solar system, evoking questions about how such planets formed and what their ultimate fate might be. The implications of microlensing extend beyond mere discovery. They offer a window into the distribution and frequency of planets in the galaxy. By analyzing microlensing data, astronomers have begun to estimate the occurrence rate of planets in the Milky Way, finding that planetary systems might be far more common than once imagined. This abundance of planets, including those in star systems vastly different from our own, suggests that planetary formation is a common outcome of star formation. It also raises exciting possibilities about the existence of Earth-like planets in the habitable zones of distant stars. Although microlensing cannot yet detect Earth-sized planets with the same regularity as it does larger, Jupiter-sized ones, technological advancements promise to improve the sensitivity of this method in the coming years. One of the most promising developments in microlensing research is NASA's planned Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Equipped with a powerful wide-field infrared survey camera, the Roman Space Telescope aims to conduct a large-scale microlensing survey of the Milky Way's central region. By monitoring millions of stars for microlensing events, the telescope will likely discover thousands of new exoplanets, including many Earth-sized and potentially habitable worlds. This mission represents a leap forward in microlensing technology and could reveal an unprecedented variety of planetary systems, from super-Earths to gas giants to rogue planets. By combining Roman's observations with data from other planet-hunting missions, scientists hope to build a comprehensive picture of the galaxy's planetary demographics, offering clues to the processes that govern planetary formation and evolution. The importance of gravitational microlensing extends to fields beyond planetary science. By studying microlensing events, researchers can gain insights into the nature of dark matter, the mysterious substance that constitutes roughly 85% of the universe's mass. Some theories suggest that dark matter might consist of compact objects such as primordial black holes, which could be detectable through microlensing. Although no definitive microlensing events attributed to dark matter have been observed, ongoing surveys continue to search for signs of such objects, which would provide invaluable data for understanding dark matter's role in cosmic structure formation. Microlensing also has applications in studying the structure of the Milky Way itself. By mapping the distribution of microlensing events across the galaxy, astronomers can infer the arrangement and composition of its stellar population, including regions obscured by interstellar dust. This information helps scientists build more accurate models of our galaxy's structure, from the dense core to the spiral arms. Through these studies, microlensing contributes to a broader understanding of the dynamics and history of the Milky Way, shedding light on how galaxies evolve over billions of years. The microlensing technique is not without challenges. Because it relies on rare and unpredictable events, microlensing detections require continuous monitoring of vast numbers of stars, often across multiple telescopes and observatories. Timing is critical, as the alignment of a star, lens, and observer can last only hours or days. Once detected, the data must be carefully analyzed to distinguish true microlensing events from other phenomena, such as variable stars or instrumental noise. Despite these hurdles, advancements in telescope technology, automated detection algorithms, and international collaboration have enabled a steady stream of microlensing discoveries, each one adding to our understanding of the cosmos. Gravitational microlensing has expanded our cosmic perspective, revealing a galaxy teeming with diverse planetary systems and strange, solitary worlds. It has shown that planets are not isolated phenomena but rather integral to the galaxy's structure, scattered throughout star clusters, spiral arms, and even interstellar space. As microlensing surveys continue to improve and new missions like the Roman Space Telescope come online, the pace of discovery will only accelerate, bringing us closer to answering fundamental questions about our place in the universe. Through microlensing, we glimpse worlds beyond our reach, each one a testament to the boundless possibilities within our galaxy. These distant planets, faint and hidden in the vastness of space, beckon us to explore and understand. Gravitational microlensing offers a rare lens through which we can peer into these mysteries, transcending the limits of distance and light to reveal the galaxy's hidden architecture. In doing so, it reminds us of the enduring human drive to seek out the unknown, to find meaning in the stars, and to ponder the infinite. Microlensing is among the most powerful tools we possess to detect exoplanets, yet it remains distinct from other planet-hunting methods, with its own set of unique advantages and limitations. Unlike techniques that rely on observing the periodic dips in starlight, or the subtle gravitational pull that planets exert on their host stars, microlensing provides a brief, yet incredibly insightful window into otherwise hidden planetary systems. This fleeting effect, which may last only a few hours to days, is caused by the gravitational field of an intervening star or planet bending and magnifying the light from a more distant background star. While it might seem improbable to rely on such perfect alignments, the vast number of stars in the galaxy increases the odds of observing these events, allowing scientists to catalog significant data about planets in otherwise unreachable parts of space. What truly sets gravitational microlensing apart is its capability to detect exoplanets located far from their host stars. While many planet-hunting methods tend to favor planets orbiting closely to their stars, microlensing is capable of detecting planets both near and far, giving scientists access to systems that defy the common planetary layouts seen in our own solar system. This has enabled the discovery of planets with orbits similar to those of Neptune and beyond, as well as planets that might otherwise be completely isolated from any star. The results of these discoveries paint a picture of planetary diversity that challenges traditional assumptions about how planetary systems form and evolve. One of the remarkable findings that microlensing has enabled is the discovery of planets in multi-star systems. Multi-star systems, where two or more stars are gravitationally bound to each other, are common in the galaxy. Until relatively recently, it was unclear how planetary systems might form in such complex gravitational environments. Yet, microlensing has helped identify planets within binary and even more complex stellar arrangements, showing that planets can form and remain stable in these systems. This capability opens up new frontiers in our understanding of planetary formation, as it suggests that planets could exist under gravitational conditions that are very different from those found in our own solar system. Some discoveries made through microlensing have broadened the parameters of habitability, prompting scientists to rethink where life-supporting conditions might arise. In 2006, for instance, a microlensing event led to the detection of OGLE 2006 BLG109LB and OGLE 2006 BLG109LC, two planets orbiting a star approximately 5,000 light-years away in the constellation Sagittarius. These planets were found to resemble Jupiter and Saturn, and their discovery suggested that giant planets could form in distant star systems much like the gas giants in our own solar system. This, in turn, sparked interest in the possibility of smaller, rocky planets forming in the habitable zones of such systems, where liquid water might exist, a key ingredient for life as we know it. The OGLE, Optical Gravitational Lensing Experiment, and MOA, Microlensing Observations in Astrophysics, collaborations have been central to microlensing research, leading the way in the detection of numerous exoplanets. These programs, based in Poland and New Zealand respectively, monitor millions of stars in the galactic bulge, searching for the telltale signs of microlensing events. By coordinating telescopic observations across multiple continents, these teams maximize the chances of capturing microlensing events, each of which offers a rare glimpse into distant planetary systems. Their work has expanded our catalog of known exoplanets and pushed the boundaries of our understanding of planetary science. One particularly intriguing aspect of microlensing is its potential to identify rogue planets, those that drift through space without a host star. These rogue planets, which might have been ejected from their original star systems or could have formed independently, challenge traditional models of planetary formation. In 2011, A team of astronomers used microlensing to suggest that there could be twice as many rogue planets as stars in the Milky Way. Such findings imply that rogue planets may be far more common than once thought, existing in a cosmic wilderness where they roam the galaxy alone. Studying these objects could reveal new insights into the forces that shape planetary systems and the extreme environments in which planets might survive. The identification of rogue planets also raises fascinating questions about the potential for life in extreme environments. Although rogue planets would not benefit from the warmth and light of a nearby star, they might still possess atmospheres capable of trapping heat or maintaining subsurface oceans, much like some of the moons in our solar system. For instance, if a rogue planet were large enough and had a thick atmosphere rich in hydrogen, it could retain enough heat to support liquid water beneath its surface. Although this scenario remains speculative, the discovery of rogue planets through microlensing has opened up discussions about the diversity of planetary environments and the adaptability of life in the universe. Microlensing's reach extends even to the outer regions of our galaxy, a realm typically beyond the capabilities of other detection methods. By magnifying the light of distant stars, microlensing can reveal planets orbiting stars in the galactic bulge or even in neighboring galaxies. This has implications not only for exoplanet science but also for understanding the formation and evolution of galaxies. By studying the frequency and distribution of microlensing events, astronomers can gain insights into the structure of the Milky Way's core and the density of stars and planets in its most crowded regions. This information is invaluable for mapping the galactic environment and understanding the forces that shape stellar and planetary populations across cosmic distances. The future of microlensing research looks particularly promising with the upcoming launch of the Nancy Grace Roman Space Telescope. With its wide-field infrared capabilities, the Roman Space Telescope will be able to survey vast regions of the galaxy with unprecedented depth and precision. This will greatly enhance our ability to detect microlensing events, including those caused by smaller, Earth-like planets. By systematically monitoring millions of stars in the galactic bulge, the Roman Space Telescope is expected to discover thousands of new exoplanets, creating a more comprehensive census of planetary systems in the Milky Way. The mission will likely transform our understanding of planetary demographics, revealing how common or rare various types of planets are, and perhaps even detecting planets that closely resemble Earth. Beyond the Roman Space Telescope, advances in artificial intelligence and machine learning are also expected to improve microlensing research. By applying sophisticated algorithms to sift through vast amounts of observational data, scientists can identify potential microlensing events more quickly and accurately. Machine learning techniques have already proven effective in automating the detection of transient astronomical events, and their application to microlensing could dramatically increase the efficiency of planet detection. This could allow astronomers to identify microlensing events that would otherwise go unnoticed, leading to the discovery of new planets and planetary systems at a faster rate than ever before. Gravitational microlensing has not only broadened our knowledge of exoplanets, but has also deepened our appreciation for the intricate dance of light and gravity in the cosmos. Each microlensing event represents a cosmic alignment of celestial bodies, a brief moment when the universe reveals one of its hidden secrets. These events are reminders of the interconnectedness of all matter in the universe, where the movement of one star or planet can reveal the existence of another, millions of light years away. The study of microlensing captures this profound relationship, using light itself as a messenger, bridging the vast distances of space to unveil planets and stars otherwise shrouded in darkness. In addition to detecting planets, microlensing has offered insights into the nature of dark matter and the distribution of matter in the galaxy. Some researchers have proposed that certain microlensing events might be caused by compact dark matter objects, such as primordial black holes. Although evidence for dark matter as a gravitational lensing source remains elusive, continued microlensing studies could one day reveal the presence of dark matter structures within or beyond our galaxy. Such discoveries would have far-reaching implications for our understanding of cosmic structure formation, the evolution of galaxies, and the overall mass-energy content of the universe. The mysteries of gravitational microlensing and the worlds it reveals are a testament to the power of human curiosity and ingenuity. Through this method, astronomers can probe the unseen and extend our reach across space and time. As we continue to refine our techniques and develop new tools, microlensing will remain an invaluable asset in our exploration of the cosmos, allowing us to uncover planets around distant stars, map the distribution of matter in the galaxy, and deepen our understanding of the forces that govern the universe. As microlensing continues to evolve, its contributions to science will only grow, furthering our quest to understand the universe and our place within it. The discoveries it yields inspire awe and curiosity, inviting us to envision the myriad worlds scattered across the cosmos. Each microlensing event offers a brief but vivid glimpse into these distant realms, where planets circle stars in silent orbits, or wander alone through the interstellar void. These discoveries remind us that, in the vast and unfathomable expanse of the universe, there is always more to explore, more to learn, and more to understand. The discoveries achieved through gravitational microlensing not only deepen our knowledge of exoplanets and cosmic structures but also offer us glimpses into the fundamental nature of space itself. Every microlensing event serves as a reminder of the interplay between light, gravity, and the bending of spacetime, a phenomenon first predicted by Albert Einstein's theory of general relativity. According to this theory, massive objects, like stars and planets, warp the fabric of spacetime, causing light to curve as it passes near them. Microlensing leverages this principle, demonstrating how even the most fleeting cosmic alignments can reveal hidden objects across vast distances, from planets orbiting distant stars to invisible celestial bodies that might otherwise remain unseen. One of the most astonishing aspects of gravitational microlensing is its ability to uncover planets in a way that defies the traditional requirements for detection. Many other exoplanet detection methods, like the transit and radial velocity techniques, depend on regular, repetitive signals. They focus on detecting planets that orbit their stars at consistent intervals, creating periodic changes in brightness or gravitational effects. Microlensing, on the other hand, requires no periodicity. It can detect planets in rare, one-time alignments, revealing planetary systems we might never have known existed. This capacity opens up an entirely new dimension of exoplanetary science, allowing us to capture snapshots of distant worlds that transcend the need for repeated observations. To further appreciate how gravitational microlensing has expanded the horizons of exoplanet discovery, consider the intriguing case of planetary systems in the galactic bulge. The galactic bulge is a dense, central region of our galaxy, home to countless stars packed closely together. Due to this crowding, observing planets in the bulge is challenging with traditional techniques, as individual stars are often indistinguishable within the dense star fields. Yet, microlensing can cut through this cosmic crowd, making it possible to detect planets around stars thousands of light-years away, nestled within the heart of our galaxy. This ability not only expands our planetary senses but also offers insights into how planetary systems might form and evolve in environments vastly different from our own Sun's quieter, suburban region of the galaxy. One of the landmark discoveries in the galactic bulge was made in 2013 when a microlensing event revealed a planet with characteristics reminiscent of Neptune orbiting a star approximately 25,000 light-years away. This finding was groundbreaking not only because it showcased microlensing's incredible reach but also because it suggested that planets similar to those in our solar system might be common throughout the Milky Way, even in regions as dense and tumultuous as the galactic core. Discoveries like these hint at the potential universality of planetary formation processes, showing us that the conditions for planet formation exist in a variety of galactic environments. Gravitational microlensing's sensitivity to distant, cold, or rogue planets provides another avenue for discovering planetary bodies that do not fit the typical mold. Planets located in the far reaches of their solar systems, beyond the so-called frost line, where volatile compounds can condense, are more difficult to detect with methods like the transit or radial velocity techniques. Microlensing, however, can detect these remote, cold worlds, offering clues about the outer architecture of planetary systems and the potential for icy exoplanets with conditions similar to the outer planets in our own solar system, such as Uranus and Neptune. By examining these distant, frozen worlds, scientists hope to learn more about how planetary systems form and evolve across different parts of the galaxy. Moreover, microlensing's capacity to detect rogue planets, those that have no host star and drift freely through space, opens new avenues for exploring planetary formation and stability. Rogue planets challenge our understanding of planetary formation, as their isolation suggests they may have been ejected from their original star systems through gravitational interactions or that they formed independently in interstellar space. Although isolated and lacking the energy input of a star, rogue planets may still harbor internal heat or even retain atmospheres capable of supporting unusual forms of life. Microlensing has already revealed a few rogue planets, and continued advancements in this field may uncover many more, further expanding our understanding of planetary diversity in the galaxy. The discovery of rogue planets has sparked considerable interest in their potential habitability. For example, some scientists speculate that if a rogue planet were large enough to retain a thick atmosphere, it might generate sufficient greenhouse effect to trap heat, thereby creating stable environments for liquid water under certain conditions. While this remains a speculative notion, the prospect of rogue planets as potential harbors for life highlights the diversity of planetary environments where life might thrive. By studying rogue planets, astronomers could gain unique insights into how life might adapt to conditions far removed from the warmth and stability of a host star. One of the profound implications of gravitational microlensing in the search for exoplanets is its role in refining our understanding of planetary formation models. In traditional models, planetary systems like ours, with a few large planets orbiting a central star, are thought to form from a rotating disk of gas and dust surrounding a young star. However, the wide variety of planetary systems detected through microlensing suggests that the conditions leading to planet formation may be more diverse and complex than these models originally proposed. By discovering exoplanets with unique orbits, unexpected companions, or configurations unlike anything seen in our own solar system, microlensing has forced astronomers to broaden their theories of how planets form and evolve across the galaxy. For example, microlensing has revealed planets that orbit their stars at vast distances, well beyond the range where traditional methods can detect them. These discoveries suggest that planetary formation processes may produce distant, gas giant-like planets more frequently than once believed, or that planets can migrate outwards from their original locations over time. Both possibilities challenge existing models, which often struggle to account for such remote planets and the mechanisms that might place them at these distances. The presence of these far-flung planets implies that planetary formation is a more varied process than we previously understood, potentially involving mechanisms that drive planets to distant orbits. The technological advancements behind gravitational microlensing are also worth noting, as they demonstrate the extent to which innovation drives discovery. Early microlensing studies relied on ground-based telescopes, with all the inherent limitations of atmospheric interference and limited observational coverage. However, modern microlensing efforts have increasingly incorporated space-based telescopes, like NASA's Spitzer Space Telescope, which in 2015 became the first telescope to observe a microlensing event from beyond Earth's orbit. This achievement allowed astronomers to observe microlensing events from two distinct vantage points, giving them a unique way to measure distances to the planets they were observing and helping to pinpoint their exact locations. Looking to the future, the Roman Space Telescope is expected to usher in a new era of microlensing. Set to launch in the coming years, the Roman telescope will feature a wide-field infrared instrument specifically designed for detecting microlensing events. This telescope will allow astronomers to observe millions of stars in the galactic bulge simultaneously, significantly increasing the number of microlensing events they can monitor, and enhancing their ability to detect low-mass exoplanets, including those similar in mass to Earth. The Roman Space Telescope's capabilities will make it possible to conduct a more detailed survey of the galactic bulge than ever before, providing a deeper understanding of exoplanet demographics across the galaxy. The Roman Space Telescope's microlensing survey is expected to produce a wealth of data that could redefine our understanding of exoplanets and their distribution in the galaxy. By enabling the detection of Earth-sized planets at much greater distances than current methods allow, the the Roman telescope will broaden our perspective on the types of planetary systems that exist in the universe. Its mission will help scientists answer fundamental questions about the prevalence of Earth-like planets, the distribution of planetary masses, and the role of galactic environment in shaping planetary systems. As microlensing continues to evolve, so too does our philosophical perspective on our place in the cosmos. The study of distant exoplanets and isolated rogue worlds raises profound questions about the nature of life and the uniqueness of our own planet. Could life exist on a rogue planet drifting alone in the darkness, or in the icy depths of a far-flung exoplanet orbiting a faint star? What does it mean if we find planets with conditions similar to Earth scattered throughout the galaxy? Each microlensing discovery brings us closer to understanding whether planets like ours are common or rare, whether life might arise under a wider array of conditions than previously imagined, and whether our existence is a cosmic anomaly or part of a larger, interconnected tapestry. Through gravitational microlensing, we witness the galaxy not only as a collection of stars but as a dynamic system of planets, moons, and rogue objects interacting through the invisible forces of gravity. Each microlensing event is a fleeting window into this cosmic dance, offering us a brief glimpse of the universe's complexity and diversity. As we look forward to future discoveries made possible by the Roman telescope and other emerging technologies, we are reminded that our journey into space has only just begun. Gravitational microlensing, with its ability to reach across unimaginable distances, serves as both a tool of discovery and a testament to the boundless curiosity that drives us to explore the unknown. In the unfolding journey of space exploration, gravitational microlensing has undeniably become one of the most exciting and indispensable tools. The technique not only allows us to detect exoplanets, but also provides essential insights into the underlying structure of the universe and the nature of objects that may otherwise elude detection. As we continue to refine and advance our observational capabilities, gravitational microlensing promises to deepen our understanding of planetary formation, star systems, and the sheer diversity of worlds that populate the Milky Way and potentially beyond. When we peer through the lens of microlensing, what we're really seeing is a universe defined by gravity's invisible yet omnipresent hand. This invisible force, bending and shaping light, creates natural magnifying glasses across vast distances. It is as if the cosmos itself has provided us with a powerful tool to amplify otherwise faint, hidden worlds, much like a cosmic detective helping us unearth clues about planets, stars, and distant galaxies. The discoveries facilitated by microlensing thus far are merely the beginning of what promises to be a profound journey into understanding the building blocks of the universe. The potential for microlensing to reveal so much hinges on several technical advances and collaborations in the field. International collaborations and survey programs have been instrumental in the success of microlensing projects. By combining data from multiple observatories, both on Earth and in space, astronomers are able to achieve a level of precision and coverage that would otherwise be impossible. The Optical Gravitational Lensing Experiment, OGLE, the Microlensing Observations in Astrophysics, MOA, collaboration, and other survey programs have made it possible to detect, monitor, and analyze thousands of microlensing events each year, generating an unprecedented amount of data on exoplanets and other cosmic phenomena. These collaborative efforts underscore the global and interdisciplinary nature of microlensing research. Observatories from around the world, whether in Japan, New Zealand, or Chile, contribute to a synchronized observation of microlensing events, maximizing the coverage and allowing for near-constant monitoring of target areas. This worldwide network of observatories enables astronomers to collect data continuously, capturing microlensing events from multiple angles and even during times when one part of the Earth experiences daylight. By uniting astronomers across the globe, gravitational microlensing studies exemplify how the search for knowledge transcends. While most microlensing discoveries involve planetary systems within our own galaxy, the technique has also proven valuable in exploring extragalactic realms. By detecting gravitational microlensing events caused by objects in distant galaxies, astronomers can study the structure and composition of these galaxies without having to rely on light from individual stars or other luminous sources. Microlensing events caused by distant galaxies allow scientists to measure the distribution of mass within these galaxies, even if the objects themselves are dark or not directly visible. This application of microlensing as a tool for studying the invisible components of galaxies provides key information on phenomena like dark matter, which makes up a significant portion of the universe's mass yet remains largely mysterious. Dark matter's influence on gravitational microlensing events has become an intriguing field of study. Since dark matter does not emit, absorb, or reflect light, it cannot be observed directly. However, its gravitational influence on surrounding objects, including light from distant stars and galaxies, can be detected through microlensing. When a dark matter structure aligns with a distant light source, it can create a microlensing effect, revealing its presence and properties indirectly. By observing the microlensing effects caused by dark matter, scientists can learn more about its distribution and behavior, inching closer to unraveling one of the greatest mysteries in cosmology. As astronomers analyze microlensing data from various parts of the galaxy and beyond, they begin to build a picture of the universe's hidden mass. Microlensing events that result from dark matter have unique signatures, differing from those caused by luminous objects like stars and planets. These differences allow scientists to isolate and study dark matter structures, gaining insights into their shapes, densities, and locations. The study of dark matter through microlensing is thus a promising avenue, providing information that may one day help solve the puzzle of dark matter's composition and origin. Furthermore, gravitational microlensing holds promise for mapping galactic populations of black holes. Black holes, being dense regions where gravity is so intense that not even light can escape, are notoriously difficult to detect without observable emissions. Microlensing, however, offers a method to indirectly detect black holes by observing their gravitational influence on the light from stars behind them. When a black hole passes in front of a distant star, it creates a microlensing event, temporarily magnifying the star's light. By analyzing these events, scientists can estimate the black hole's mass and location, contributing to our understanding of black hole populations and their distribution across the galaxy. This capability to detect black holes is particularly exciting because it does not rely on the black hole's interaction with other matter. Traditionally, black holes are discovered through the emissions generated when they interact with nearby gas or other objects, creating powerful X-ray or gamma-ray emissions. However, isolated black holes without such accretion sources are virtually invisible by traditional observational standards. Microlensing can reveal these hidden black holes, providing a more complete picture of black hole demographics, including quiet black holes that might otherwise remain undetected. The role of microlensing in studying black holes also complements our understanding of gravitational waves. As black holes collide or merge, they produce gravitational waves, ripples in spacetime detectable by observatories like LIGO and Virgo. Together, microlensing and gravitational wave astronomy create a multidimensional approach to studying black holes, combining indirect observations of their gravitational influence with direct detections of their energetic mergers. This dual approach enriches our understanding of black hole formation, evolution, and the influence they exert across galactic and even intergalactic scales. Beyond the boundaries of our galaxy, microlensing can also probe intergalactic space. This sparsely populated region between galaxies, known as the cosmic void, is thought to contain dark matter and other low-density material. By observing microlensing events in intergalactic space, scientists can study the distribution of this unseen matter, mapping its structure and understanding its role in the overall cosmic web that connects galaxies across the universe. This application of microlensing not only aids in the search for exoplanets, but also enriches our knowledge of the universe's large-scale structure. The cumulative impact of gravitational microlensing on our understanding of the cosmos is profound. Each microlensing event is a snapshot of a unique moment, capturing fleeting interactions that bring the distant, the dark, and the hidden into view. From revealing planets in the galactic bulge to detecting rogue planets, mapping dark matter, and uncovering isolated black holes, gravitational microlensing serves as a reminder of the universe's intricacy and interconnectedness. It is a technique that, through its dependence on alignment, speaks to the delicate balances and synchronizations inherent in the cosmos. In the coming years, as observatories like the Roman Space Telescope enhance our capacity to study microlensing events, the pace of discovery will likely accelerate. The vast troves of data that will emerge from the Roman Telescope's microlensing survey will not only expand our planetary census but will also challenge and refine our theories about how planetary systems, galaxies, and even the universe itself are structured and evolve. Each new microlensing event will add a piece to the puzzle, bringing us one step closer to a comprehensive understanding of the universe and our place within it. As we stand on the cusp of this new era of discovery, gravitational microlensing exemplifies the potential of human ingenuity and collaboration. Through complex instrumentation and international partnerships, we have developed a tool that reaches across unimaginable distances, capturing light from the farthest corners of space. The study of gravitational microlensing is more than just an exploration of distant planets and dark objects. It is a testament to humanity's relentless pursuit of knowledge and our innate desire to explore the unknown. Gravitational microlensing, with its ability to reveal hidden planets, rogue worlds, and mysterious dark matter, symbolizes the frontier spirit that has always driven scientific progress. Each time we observe a microlensing event, we are reminded of the vastness of space and the myriad mysteries that lie beyond our current understanding. Through these observations, we glimpse a universe rich with diversity, complexity, and beauty, a universe that continues to captivate our imagination and inspire our quest for discovery. The journey of understanding gravitational microlensing and its implications for planetary science and cosmology continues to push the boundaries of what we know about the universe. Each microlensing event, whether it reveals a distant exoplanet or offers a glimpse of dark matter's elusive presence, brings us closer to grasping the vast web of connections and forces that hold the universe together. At its core, gravitational microlensing serves as a bridge between theory and observation, enabling scientists to connect mathematical predictions with tangible discoveries. The predictive power of microlensing is grounded in Einstein's theory of general relativity, which laid the foundation for understanding how mass distorts spacetime. When large celestial objects, such as stars or black holes, pass in front of a distant light source, they cause a gravitational lensing effect that magnifies and alters the light's path. This principle is at the heart of gravitational microlensing, where the lens is the foreground object, and the magnified source is the background star or galaxy. What makes microlensing particularly powerful is its capacity to reveal low-mass objects, such as exoplanets, by observing even slight deviations in the light curve, providing insight into the mass and distance of objects that are otherwise invisible. Microlensing, therefore, offers astronomers a precise yet indirect method to map unseen realms of the universe. Unlike transit or radial velocity methods, which depend on a planet's gravitational pull on its host star or the regular dimming of starlight, microlensing detects planets irrespective of their position relative to the host star. This allows astronomers to detect planets in a wider range of orbits, including distant gas giants and rogue planets that wander freely without a parent star. As microlensing doesn't rely on the light from the planet itself, it opens up a vast observational window to study faint and cold planets, challenging the idea that planetary systems need to be well lit or tightly bound for us to observe them. The discovery of free-floating or rogue planets through microlensing exemplifies the method's ability to reveal new categories of celestial bodies. Rogue planets are planetary mass objects that drift through space without a star, likely ejected from their original solar systems by gravitational interactions with other large bodies. With no star to illuminate them, these dark wanderers are practically undetectable by conventional means. Yet, gravitational microlensing can identify them by the gravitational tug they exert on background starlight. This discovery has led scientists to consider whether rogue planets could outnumber bound planets in the galaxy, reshaping theories of planetary formation and system evolution. The presence of potentially trillions of rogue planets in the Milky Way raises profound questions about the distribution of matter in our galaxy. Unlike bound exoplanets that orbit a host star, rogue planets occupy interstellar space, contributing to a hidden mass that isn't easily accounted for in galactic models. If rogue planets are as numerous as initial studies suggest, their collective mass could impact our understanding of galactic gravitational fields, potentially influencing star formation rates and the dynamics of galactic arms. Microlensing, in this sense, not only reveals individual objects but also provides insights into the structural makeup of our galaxy, informing the models that predict how stars, planets, and dark matter interact on cosmic scales. While microlensing has already revealed extraordinary findings, the technique's future potential is even more exciting. Upcoming missions like NASA's Nancy Grace Roman Space Telescope are designed to expand our microlensing capabilities significantly. With its wide-field infrared observations, the Roman telescope is expected to capture thousands of microlensing events, including those that involve planetary systems. By conducting a massive survey of the galactic bulge, where star density is highest, the Roman mission will offer an unprecedented view of planetary systems within the densest parts of our galaxy. This will allow astronomers to test whether planetary systems are more common in denser stellar environments, and to explore the relationship between star formation and planetary evolution on a grand scale. The Roman Space Telescope's survey will not only enhance our understanding of planetary systems, but will also help refine the models of stellar and galactic evolution. Observing microlensing events in the galactic bulge provides critical data for mapping the distribution of stars, planets, and dark matter in our galaxy's core. By combining microlensing data with models of stellar population dynamics, scientists will gain a clearer picture of the Milky Way's structure, including its gravitational potential and the movement of stars within its dense core. The ability to observe planetary systems in various parts of the galaxy also enriches our understanding of how different environments impact planet formation and survival, offering clues about the diversity of planetary systems across the universe. Beyond its applications within the Milky Way, microlensing could extend our reach to neighboring galaxies. Although detecting individual exoplanets in distant galaxies remains challenging, microlensing events caused by massive objects in nearby galaxies, like Andromeda, can still yield information about their dark matter content and overall mass distribution. This line of research could reveal how galaxies evolve over cosmic time, shedding light on the processes that shape galaxies and their central black holes. As we observe microlensing events across intergalactic distances, we start to glimpse the large-scale structure of the universe, from the clustering of galaxies to the web of dark matter that spans cosmic space. The potential of microlensing for unveiling the universe's hidden masses also connects it to one of the most profound questions in cosmology: the nature of dark matter. Dark matter, the invisible substance thought to make up about 85% of the universe's mass, doesn't emit or absorb light, making it difficult to observe directly. However, dark matter interacts gravitationally, and this interaction can be detected through microlensing. Some microlensing events, especially those involving faint or invisible lenses, may hint at the presence of dark matter structures, such as MACHOs, massive compact halo objects, which could include black holes, neutron stars, or dense clumps of unseen matter. By studying these events, astronomers hope to map the distribution of dark matter within and between galaxies, providing crucial data to understand its role in the cosmos. The interplay between dark matter and microlensing has sparked new research avenues that may eventually help solve one of science's biggest mysteries. If dark matter does indeed clump in certain ways, creating compact objects or halos, then microlensing surveys may occasionally reveal these halos by capturing brief lensing events that deviate from typical patterns. This would not only confirm the presence of dark matter but also help constrain its properties, potentially revealing whether it consists of exotic particles or more familiar objects that have escaped detection. Microlensing, in this way, serves as a gateway to a realm of the universe that, while unseen, has profound implications for everything from galaxy formation to the ultimate fate of cosmic expansion. In addition to shedding light on dark matter, microlensing contributes to our understanding of stellar remnants, objects left over from the deaths of stars, like black holes, white dwarfs, and neutron stars. Traditional methods of observing these remnants often rely on high-energy emissions, such as X-rays from black holes accreting matter. However, not all stellar remnants emit such radiation. Many black holes, for instance, are quiet, meaning they are not actively accreting material, and thus don't produce observable emissions. Microlensing provides a rare opportunity to detect these quiet remnants by observing their gravitational impact on passing starlight. By mapping the distribution of such remnants, we gain insight into the life cycles of stars and the processes that drive stellar death across the galaxy. The detection of quiet black holes through microlensing has implications for both stellar evolution and the study of gravitational waves. Black hole mergers, which produce detectable gravitational waves, are influenced by the number and distribution of quiet black holes within star clusters and galaxies. Understanding how black holes form and evolve in isolation helps researchers model these mergers and predict where and how often they might occur. With microlensing, we can map black hole populations in a way that complements gravitational wave observations, giving us a fuller picture of the life cycles of these enigmatic objects. As microlensing technology advances, it may also play a role in detecting primordial black holes, hypothetical black holes that could have formed in the early universe, potentially contributing to dark matter. These primordial black holes would be far smaller than the stellar mass black holes created by collapsing stars, but if they exist in sufficient numbers, they could account for a portion of dark matter. Detecting them would require extraordinarily sensitive microlensing observations, capable of capturing minute fluctuations in starlight over vast distances. Yet, if primordial black holes are indeed part of the dark matter mystery, microlensing could one day offer the first observational evidence of their existence. Gravitational microlensing thus provides a window into both the origins of planetary systems and the larger cosmic mysteries that define the universe. It bridges the micro and macro scales of the cosmos, revealing planets, dark matter, black holes, and possibly even clues to the earliest epochs of cosmic history. Each microlensing event, each flicker of light from a distant star, tells a story about the unseen forces shaping the universe. In a way, microlensing allows us to see the unseeable, turning the galaxy itself into a laboratory for discovery. The growing field of microlensing research is a testament to human curiosity and our drive to uncover the unknown. From ancient stargazers to modern-day astronomers, the desire to understand the night sky has propelled human civilization forward, pushing us to build increasingly powerful telescopes, launch space missions, and develop theoretical frameworks that stretch our comprehension of reality. Gravitational microlensing stands as one of the most remarkable achievements in this quest, a technique that leverages the very fabric of space-time to reveal the universe's hidden treasures. As we continue exploring the impact of gravitational microlensing, it's clear that this technique exemplifies the power of scientific innovation to unlock secrets of the cosmos. By tracing the bending of light, microlensing extends our senses into the far reaches of space, revealing not only planets and stars but also the invisible scaffolding of dark matter that holds galaxies together. This delicate dance of light and gravity, guided by Einstein's equations, has transformed microlensing into a tool that rivals even the most advanced direct imaging and spectroscopic methods for planetary discovery. One of the most exciting aspects of gravitational microlensing is its ability to provide a more statistically representative sample of planetary systems. Unlike the radial velocity and transit methods, which often favor the detection of massive planets in close orbits, microlensing offers an unbiased look at planets at a variety of distances from their host stars. This has enabled scientists to catalog planets that reside in the so-called cold zone, far from the warmth of their stars. Many of these planets resemble Jupiter and Saturn, gas giants that may harbor their own systems of moons, raising questions about whether such moons could host conditions for life, even at extreme distances from a star. Microlensing has thus introduced the possibility of icy moons and distant ocean worlds in the cold reaches of exoplanetary systems. Given the discoveries of potentially habitable moons within our own solar system, such as Europa and Enceladus, which contain subsurface oceans despite their distance from the Sun, scientists now speculate about similar conditions around exoplanetary moons. With microlensing allowing us to glimpse these gas giants and their potential satellites, the search for life has expanded beyond the classic habitable zone to include worlds where internal heat sources, such as tidal flexing or radioactive decay, might support life. These insights challenge our understanding of habitability, prompting a re-evaluation of what constitutes a life-sustaining environment. As microlensing surveys continue, they reveal not only new planets but also diverse planetary architectures that defy traditional models of solar system formation. For example, while the solar system has a clear distribution of terrestrial planets close to the Sun and gas giants farther away, many microlensing discovered systems display different patterns, with gas giants and super-Earths found in unexpected orbits. Such discoveries push planetary formation theories to account for a broader range of outcomes, suggesting that each planetary system may be as unique as a fingerprint. This diversity in planetary arrangement may ultimately inform the search for Earth-like planets, helping scientists identify systems that are more likely to resemble our own. Microlensing's ability to capture faint, far-off planets also enables astronomers to study galactic stellar populations indirectly, offering insights into the galactic structure itself. As microlensing events occur predominantly in densely packed regions, like the galactic bulge, they provide an opportunity to map the gravitational influences of stars within these regions, painting a picture of stellar distributions across the Milky Way. By gathering data from repeated microlensing surveys, scientists can construct models of the galactic bulge's mass and structure, discerning details about its star density, potential black hole populations, and dark matter distribution. Each microlensing observation thus serves as a data point, building a more complete map of our galaxy's gravitational landscape. Interestingly, microlensing may also provide a means to detect more exotic objects, such as hypothetical dark matter candidates like primordial black holes or weakly interacting massive particles, WIMPs. Though not yet observed, these entities are theorized to form clumps within galaxies and could manifest as subtle distortions in microlensing events. Detecting such distortions would add evidence to dark matter theories, offering a glimpse into a fundamental component of the universe that has otherwise eluded direct observation. The fact that microlensing can potentially reveal dark matter aligns with its broader role in cosmology. It serves as a gateway to understanding not only visible matter but also the unseen forces shaping galactic dynamics. Furthermore, microlensing discoveries have implications for the study of galactic evolution and the origins of planetary systems. As we detect planets in various stages of formation or located in environments with different metallicities, the presence of elements heavier than hydrogen and helium, microlensing helps us determine how conditions like metal abundance influence planet formation. Studies suggest that metal-rich stars are more likely to host gas giants, while metal-poor environments may yield smaller, rocky planets. By cataloging exoplanets across diverse galactic environments, microlensing offers insight into how different regions of the galaxy, from the dense bulge to the thin disk, contribute to planetary diversity. One of the fascinating revelations from microlensing surveys is that planets might not be a rare feature of the universe but rather a common byproduct of star formation. As more exoplanets are identified through microlensing, the prevailing theory that planets form as a natural part of star system evolution gains support. This notion has profound philosophical implications, suggesting that planetary formation, and perhaps even the conditions necessary for life, might be a widespread phenomenon across the cosmos. If planets are indeed abundant throughout the galaxy, the possibility of habitable worlds, or at least environments capable of supporting life, becomes more plausible on a cosmic scale. The implications of these discoveries extend beyond planetary science and touch on our understanding of life's potential in the universe. As microlensing uncovers planets in configurations vastly different from our solar system, it challenges us to broaden our conceptions of habitability. Planets orbiting dim, red dwarf stars or free-floating rogue planets with internal heat sources could conceivably support microbial life in environments that, while extreme, are not impossible. The sheer diversity of planetary environments revealed by microlensing reinforces the idea that life, if it exists elsewhere, may thrive under conditions that we currently deem unlikely. Looking forward, advancements in technology promise to refine and expand microlensing capabilities, enabling even deeper and more detailed surveys. As ground-based telescopes increase in sensitivity and upcoming space missions are equipped with powerful wide-field cameras, the resolution of microlensing observations will improve. This could lead to an era of microlensing, precision science, where we are able to determine detailed characteristics of exoplanets, such as their atmospheric composition, surface conditions, and even potential biosignatures. This level of detail would mark a transformative step in exoplanetary science, allowing us to characterize planets and moons across the galaxy with unprecedented specificity. In addition, machine learning and artificial intelligence are set to play a significant role in analyzing the massive data sets generated by microlensing surveys. Detecting microlensing events requires distinguishing between genuine signals and background noise, a task well-suited for AI algorithms capable of sifting through enormous amounts of data quickly and accurately. By automating the detection of microlensing events, AI-driven systems can expedite the discovery of new planets, streamlining the process from raw observation to confirmed exoplanet cataloging. This automation will enable researchers to focus on interpreting results, fostering a rapid cycle of discovery and analysis. As microlensing continues to reveal the hidden architecture of the universe, it also fuels public fascination with space and the possibility of other worlds. Each discovery made through microlensing brings humanity closer to answering some of our oldest questions. Are we alone in the universe? Are there other planets out there with the potential to harbor life? And what does the arrangement of these distant worlds tell us about our place in the cosmos? The public's excitement about space exploration is reflected in the support for space missions and scientific funding, demonstrating how discoveries in planetary science resonate far beyond academic circles. The mystery and wonder associated with gravitational microlensing echo humanity's enduring quest for knowledge and exploration. As one of the few methods capable of detecting planets in the darkest, most distant reaches of our galaxy, microlensing serves as a powerful reminder of the ingenuity required to understand the universe. With each flicker of light that hints at an unseen planet or an ancient star, microlensing extends our reach across time and space, bridging the vastness of the cosmos with the curiosity that drives scientific inquiry. Ultimately, gravitational microlensing is a testament to the power of observation and the beauty of indirect discovery. It reveals that even the faintest gravitational signals carry profound information about the universe, allowing us to map the unseen and imagine the unimaginable. In the pursuit of exoplanets and beyond, microlensing stands as a pioneering technique, one that not only charts the paths of planets and stars but also inspires the next generation of scientists, explorers, and dreamers to look to the skies and wonder. Each microlensing event brings us closer to understanding the galactic tapestry, woven from planets, stars, and the mysterious forces that bind them. In the end, gravitational microlensing is more than a method, it's a bridge to the unknown, a tool that enables us to perceive the universe's hidden harmonies and uncover the celestial secrets that lie far beyond the reach of ordinary sight. As we delve further into the significance of gravitational microlensing, it's essential to recognize how this technique not only aids in the discovery of exoplanets, but also deepens our understanding of cosmic phenomena on a universal scale. The beauty of microlensing lies in its ability to unveil hidden aspects of the cosmos, often providing unexpected insights into the structure and distribution of matter across the galaxy. For example, microlensing events can reveal subtle gravitational influences from objects that would otherwise remain undetected, such as rogue planets, or even black holes. These discoveries contribute to a broader narrative about how galaxies are structured and how they evolve over time. One of the most intriguing applications of microlensing in recent years has been in the search for rogue planets. Planets that wander freely through space without orbiting a star. These rogue planets, also known as free-floating planets, are difficult to detect through traditional methods since they emit little to no light and do not transit any star. However, when a rogue planet passes in front of a distant star, it can produce a distinct microlensing signal, offering a rare opportunity to study these mysterious objects. Through such events, scientists have been able to estimate that rogue planets might be as numerous as the stars in our galaxy, an astonishing revelation that challenges conventional models of planetary formation and stability. In addition to rogue planets, gravitational microlensing has also shed light on other elusive celestial bodies. For example, the technique has been employed to search for intermediate mass black holes, which are theorized to bridge the gap between stellar mass black holes and the supermassive black holes found at galactic centers. Detecting these intermediate mass black holes is difficult, as they are often too faint to be observed directly. However, if one of these black holes passes in front of a star or another object, it can produce a detectable microlensing effect. These events help astrophysicists probe the existence and distribution of black holes, offering insights into their role in galactic evolution and the dynamics of dark matter within galaxies. Another significant contribution of microlensing to cosmic science involves the study of stellar populations in different regions of the Milky Way. By analyzing microlensing events, scientists can estimate the density and distribution of stars in areas such as the galactic bulge, which is densely populated and difficult to observe with direct imaging methods. Microlensing enables astronomers to map the galactic bulge's gravitational profile, providing a clearer picture of star formation rates, metallicity variations, and stellar ages within this region. Such information is essential for understanding how the Milky Way formed and evolved over billions of years, as well as for comparing it to other galaxies. The impact of microlensing extends to dark matter research as well. Dark matter, an invisible substance that makes up roughly 85% of the matter in the universe, has remained one of the greatest mysteries in cosmology. Though we cannot observe dark matter directly, its gravitational effects can influence microlensing events. By studying the frequency and distribution of microlensing signals in regions where dark matter is thought to be concentrated, such as the halos of galaxies, scientists can gain indirect insights into its presence and behavior. Observing the influence of dark matter on microlensing events allows researchers to refine their models of how dark matter interacts with regular matter, moving us closer to understanding its role in shaping cosmic structures. Furthermore, the continued development of microlensing technologies and techniques promises to refine our understanding of planetary diversity within the Milky Way. As microlensing telescopes become more advanced, they allow scientists to capture shorter, fainter microlensing events that might otherwise go unnoticed. This increased sensitivity is essential for detecting smaller planets, especially those that may resemble Earth in size and composition. By detecting a wider variety of planets, from massive gas giants to rocky Earth-like planets, microlensing broadens our view of planetary formation and composition, enhancing our understanding of how planets evolve under varying conditions. Microlensing has also inspired collaborative research efforts between ground-based and space-based observatories. For instance, missions like NASA's Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission aim to leverage the microlensing technique from space, free from atmospheric distortions that can hinder ground-based observations. These space-based observatories will bring a new level of precision to microlensing observations, potentially detecting smaller and more distant exoplanets than ever before. Such collaborations promise to yield high-resolution data that could clarify planetary characteristics, such as mass, radius, and even atmospheric composition in certain cases. The implications of these advancements for planetary science are profound. As we gather more data on a diverse array of exoplanets, we refine our models of planetary formation and evolution, allowing us to draw comparisons between planetary systems across the galaxy. These comparisons might one day reveal commonalities in the formation processes that give rise to habitable worlds, offering clues about the likelihood of life elsewhere in the cosmos. Moreover, the insights gained through microlensing could provide a clearer understanding of the distribution of planetary resources, such as water and organic compounds, that are essential for life as we know it. As microlensing continues to evolve, it could play a role in the quest for biosignatures, chemical signs of life in a planet's atmosphere. Although direct detection of biosignatures remains beyond the current capabilities of microlensing, future developments in space-based microlensing technology, combined with advancements in spectroscopy, might one day allow us to detect atmospheric gases like oxygen and methane in distant planets. Discovering such biosignatures would be a groundbreaking achievement, one that would suggest the presence of life beyond Earth and potentially reshape humanity's understanding of its place in the universe. Another intriguing possibility is the use of microlensing in multi-messenger astronomy, a field that combines observations across different types of signals, such as gravitational waves, neutrinos, and electromagnetic waves, to study cosmic events. Microlensing could serve as a complementary tool in these studies, helping to locate and characterize celestial objects that generate gravitational waves, such as merging black holes or neutron stars. By integrating microlensing data with gravitational wave observations, scientists could gain a more complete understanding of the environments and conditions surrounding these extreme events. Beyond scientific discovery, the application of microlensing has captured the public's imagination, drawing attention to the wonders of space and the possibilities of finding other worlds. As each new exoplanet is identified, interest in space exploration and astronomy grows, fostering a sense of curiosity and wonder. The captivating nature of microlensing-based discoveries, combined with the mystery of unseen planets and cosmic phenomena, serves to inspire the next generation of scientists and enthusiasts. By making these distant worlds more accessible to human understanding, microlensing brings us closer to answering age-old questions about the universe and our place within it. The legacy of gravitational microlensing, therefore, is not only its technical achievements and scientific contributions but also its role in expanding our perspective of the cosmos. It challenges us to imagine a universe where planets are abundant, each with its unique story, orbiting stars in ways that defy easy classification. Microlensing provides a means to explore this vast diversity, encouraging us to think beyond the limitations of our own solar system and to consider the myriad possibilities that lie among the stars. In the coming decades, as technology advances and our observational reach extends further into the galaxy, microlensing will continue to be a pivotal tool in the search for exoplanets and the quest to understand the distribution of matter across the universe. Each microlensing event serves as a reminder of the hidden structures and forces that shape our galaxy, from the delicate dance of gravitational fields to the distribution of dark matter. This ongoing exploration underscores humanity's enduring desire to seek answers, to look beyond what is visible, and to pursue knowledge across the vast, silent reaches of space. Ultimately, gravitational microlensing exemplifies the spirit of discovery that drives astronomy forward. By harnessing the subtle influence of gravity, microlensing reveals the invisible, bringing light to the darkest corners of the galaxy and illuminating worlds that might otherwise remain forever beyond our grasp. With each new discovery, we gain not only a greater understanding of the universe but also a renewed appreciation for the interconnectedness of all things, a cosmic tapestry woven from light, gravity, and the boundless curiosity that propels us to explore the unknown. In the vast tapestry of cosmic phenomena, gravitational microlensing stands as a beacon, guiding our understanding of the galaxy's hidden structure and unveiling new worlds that exist beyond the reach of traditional telescopes. As we reflect on the groundbreaking achievements of microlensing thus far, it becomes clear that this technique holds potential for even greater discoveries in the future. Imagine a galaxy where countless exoplanets drift silently, each with its unique environment, geological features, and atmospheric makeup. Through microlensing, we can glimpse these planets and begin piecing together the story of how they came to be, their potential for habitability, and even the processes that might lead to the development of life. Microlensing works by exploiting the natural curvature of spacetime, predicted by Einstein's theory of general relativity. When a massive object, like a star or planet, passes in front of a more distant star, the light from the distant star bends around the nearer object due to its gravitational field. This bending of light amplifies the background star's brightness in a distinctive pattern that can be observed and analyzed. The lens, created by the nearer object, acts like a cosmic magnifying glass, allowing astronomers to detect the presence of planets even when they are many light years away and would otherwise be invisible. This magnification effect is temporary, lasting only as long as the alignment between the two objects holds. But in that brief window, astronomers can gather crucial information about the lensing object. By studying the specific way the light curves, they can determine whether a planet is present, estimate its mass, and even glean information about its distance from its host star. For a planet orbiting a distant star, this alignment and magnification reveal details that would be unattainable through any other means. As a result, microlensing has emerged as a powerful technique for detecting not just any planets, but those that orbit far from their stars, as well as free-floating planets that do not orbit stars at all. One of the most remarkable aspects of microlensing is its ability to find planets in environments that are otherwise challenging to explore. For example, microlensing has been instrumental in identifying exoplanets in the galactic bulge, a densely populated region at the center of the Milky Way. This region is crowded with stars, making it difficult for telescopes to isolate individual stars and observe transits, or radial velocity changes. However, microlensing events offer an alternative way to study planets in this area, as they only require that the star-planet system align with a more distant light source. Through these events, astronomers have been able to detect planets in the galactic bulge, providing valuable data on planetary formation in high-density stellar environments. The search for planets in the galactic bulge also sheds light on the history of the Milky Way. This central region of our galaxy is thought to be one of the oldest, with stars that are billions of years old. By studying the planets found there, astronomers can investigate whether planetary formation has been ongoing since the galaxy's early days or if it peaked during specific epochs. This information, in turn, helps refine our models of galactic evolution and the role that planets have played in shaping the environments within our galaxy. Another noteworthy application of microlensing is in the search for planets orbiting low-mass stars and brown dwarfs. These celestial bodies, often referred to as failed stars, lack the mass necessary to ignite hydrogen fusion in their cores, leaving them faint and difficult to observe. Traditional methods like the transit method or radial velocity are less effective with these objects due to their low brightness. However, microlensing provides an indirect way to detect planets around these dim hosts. If a brown dwarf or low-mass star passes in front of a distant star, the microlensing event can reveal the presence of orbiting planets, even if the host is almost invisible itself. This capability has broadened our knowledge of where planets can form and survive, showing that planetary formation can occur even around objects with minimal stellar energy output. In a broader sense, microlensing has helped redefine our understanding of planetary abundance. Observations from microlensing surveys have indicated that planets may be far more common than previously thought. In some studies, the frequency of planets per star has been estimated to exceed 1, suggesting that nearly every star could have at least one planet, if not more. This revelation has profound implications for our understanding of the universe, hinting that planetary formation is a natural byproduct of star formation and that planets are a ubiquitous feature of the galaxy. Consequently, the likelihood of finding habitable planets, and perhaps even life, has increased, sparking renewed interest in the search for Earth-like exoplanets. The use of gravitational microlensing in the search for potentially habitable exoplanets is one of the most exciting frontiers in planetary science. While microlensing alone cannot reveal an exoplanet's atmospheric composition, it provides a crucial first step, detecting planets in a variety of environments, including those that might harbor conditions suitable for life. By expanding the inventory of known exoplanets, microlensing offers a foundation for future missions that could investigate the atmospheres of these planets more closely. Combined with spectroscopy from other observatories, such as the James Webb Space Telescope, microlensing discoveries could one day lead to the identification of biosignature gases in exoplanet atmospheres, suggesting the presence of life. The potential for future advancements in microlensing technology is vast. Planned missions like NASA's Nancy Grace Roman Space Telescope are expected to revolutionize the field by observing thousands of microlensing events from space. The Roman telescope will offer unprecedented precision and sensitivity, enabling the detection of smaller and more distant planets than ever before. Operating from space eliminates atmospheric interference, providing clearer, uninterrupted views of distant stars. With its advanced instrumentation, the Roman telescope could detect planets with masses as small as that of Mars, extending the range of detectable planets and offering a more detailed picture of planetary distribution across the galaxy. Another exciting development is the prospect of combining microlensing with other detection methods to confirm the existence of exoplanets. While microlensing excels in detecting planets at great distances, other methods, like the transit technique, offer different types of data, such as measurements of a planet's atmosphere and temperature. By cross-referencing microlensing events with data from transits, radial velocity, or even direct imaging, astronomers can build a comprehensive profile of certain exoplanets, enriching our understanding of their characteristics and potential habitability. Beyond the search for individual planets, gravitational microlensing also offers a unique method for probing the overall structure of the Milky Way. Through large-scale microlensing surveys, scientists can estimate the distribution of stars and planets in different regions of the galaxy, from the dense core to the thinly populated outer disk. These surveys not only map out where stars and planets are located but also reveal how mass is distributed throughout the galaxy. This information is essential for understanding the galactic gravitational potential, which influences the orbits of stars, the motion of interstellar gas, and even the dynamics of dark matter within our galaxy. In addition to mapping the galaxy, microlensing has become an important tool in the study of dark matter. Dark matter is an enigmatic substance that does not emit or absorb light but exerts a gravitational influence on visible matter. Although dark matter makes up a significant portion of the universe's mass, it remains invisible and undetectable through traditional methods. However, its gravitational effects can be inferred through microlensing events. By analyzing the frequency and characteristics of microlensing events in regions rich in dark matter, such as galactic halos, astronomers can gain indirect insights into the presence and behavior of this elusive substance. The study of dark matter through microlensing is a promising field with the potential to unlock fundamental mysteries about the nature of matter and the universe. If scientists can determine how dark matter is distributed in relation to stars and other visible matter, they might be able to identify patterns that reveal its composition and behavior. This knowledge could lead to breakthroughs in our understanding of galaxy formation, the large-scale structure of the cosmos, and the fundamental forces that govern the universe. As the field of microlensing continues to evolve, it offers a window into a universe that is as rich in diversity as it is in mystery. Every exoplanet discovered through microlensing tells a story of cosmic formation, survival, and perhaps even the potential for life. Through microlensing, we are not only cataloging planets but also uncovering the broader cosmic ecosystem in which these planets exist. This ecosystem includes rogue planets drifting through the void, ancient stars at the heart of the galaxy, and dark matter clumping in mysterious halos, each contributing to the grand narrative of the Milky Way. The future of microlensing promises to expand our view of the universe, offering an ever deeper understanding of the diversity and complexity that defines it. With each new discovery, microlensing continues to push the boundaries of human knowledge, encouraging us to contemplate questions that reach beyond the limits of our own solar system and into the farthest corners of the galaxy. This journey of exploration, fueled by curiosity and a relentless drive to uncover the unknown, represents the essence of humanity's quest for understanding. The potential of gravitational microlensing extends beyond simply discovering new worlds. It has become a key instrument in unveiling the profound mysteries of the cosmos and in reshaping our understanding of planetary formation, galactic structure, and the unseen influences at work within our universe. The growing sophistication of microlensing surveys, combined with the advent of powerful telescopes like the upcoming Nancy Grace Roman Space Telescope, promises to elevate this technique to a level of precision previously unimaginable. As we anticipate the launch of the Roman telescope, astronomers and scientists alike are preparing for an unprecedented era of exoplanetary exploration. Unlike ground-based observations, which are limited by atmospheric conditions and the interference of Earth's own light pollution, the Roman telescope will operate from space, enabling clear and consistent monitoring of microlensing events. Its advanced detectors and high-resolution imaging capabilities will enhance sensitivity to even the faintest of signals, allowing it to detect low-mass planets that are typically difficult to observe, such as those comparable in size to Mars. This sensitivity is critical for expanding our understanding of planetary systems, especially those that differ from our own solar system, where smaller terrestrial planets are common. The Roman telescope's field of view is also vast compared to existing telescopes, allowing it to monitor large sections of the sky simultaneously. This broad scope will enable it to capture more microlensing events and provide a more comprehensive sample of exoplanets across various regions of the galaxy. With its capacity to detect planets at a range of distances from their host stars, including those that orbit far out in the cold reaches of their systems, the Roman telescope will likely uncover a diverse array of planetary types and configurations. Such diversity is essential for testing theories of planetary formation and migration, shedding light on the many ways that planets can form, evolve, and settle into stable orbits. One of the intriguing aspects of microlensing is its ability to detect planets that exist in unconventional orbits, including rogue planets that wander alone through the galaxy without a parent star. These free-floating planets are believed to have formed within a planetary system and were subsequently ejected due to gravitational interactions or instability. By studying rogue planets, scientists can gain insights into the dynamics of planetary systems and the violent processes that can disrupt them. Some estimates suggest that there could be as many, if not more, rogue planets as there are stars in the galaxy, which implies that planetary formation is an incredibly common occurrence, and that systems with multiple planets are prone to gravitational interactions that can result in ejection. Rogue planets are particularly fascinating because they challenge our conventional understanding of planetary environments. Without the warmth of a nearby star, these planets are shrouded in darkness, their atmospheres frozen and inactive. However, some scientists have proposed that these planets could harbor subsurface oceans or geothermal heat sources, which might sustain primitive forms of life. This possibility expands our conception of habitability, suggesting that life could potentially exist in environments vastly different from those we find on Earth. The discovery and study of rogue planets could, therefore, have profound implications for astrobiology and our search for life in the cosmos. In addition to rogue planets, gravitational microlensing has begun to reveal planets around stellar remnants, such as white dwarfs. These stellar corpses are the remnants of stars that have exhausted their nuclear fuel and shed their outer layers, leaving behind a dense, dim core. While white dwarfs lack the energy output of main-sequence stars, they retain enough gravity to host planets, and microlensing events have shown that planets can indeed orbit these ancient objects. By studying planets around white dwarfs, scientists can investigate the long-term stability of planetary orbits and the survival of planets through the final stages of stellar evolution. Understanding these interactions can provide a glimpse into the future of our own solar system, as the Sun is expected to end its life as a white dwarf in several billion years. The detection of planets around white dwarfs also raises questions about planetary formation and destruction. Did these planets form around the white dwarf after it lost its outer layers? Or did they somehow survive the tumultuous process of the star's transformation? If they survived, this resilience could mean that planets around white dwarfs might be more common than previously thought, representing a distinct population of exoplanets that endured despite the dramatic changes of their host stars. By probing these resilient worlds, astronomers can piece together the life cycles of planetary systems and gain insights into the ultimate fate of planets. Moreover, the study of planets around white dwarfs and other stellar remnants provides a unique opportunity to explore potential biosignatures under extreme conditions. Though the chance of finding life in such systems is low, any indication of atmospheric or surface activity would open up a new realm of astrobiological research, potentially challenging our understanding of the prerequisites for life. For instance, planets orbiting white dwarfs might experience tidal heating or other forms of energy input that could sustain chemical reactions, making them intriguing, if unlikely, targets for future exploration. One of the most exciting future prospects of gravitational microlensing lies in its potential synergy with other observational techniques. For instance, while microlensing can reveal the existence of distant planets, it does not provide information about the planet's atmosphere or surface conditions. However, missions such as the James Webb Space Telescope, JWST, are equipped to perform spectroscopic analysis, which can detect and analyze the atmospheres of exoplanets during transits or through direct imaging. By combining the findings of microlensing with JWST's capabilities, scientists can select microlens planets for follow-up observations, potentially examining their atmospheres for biosignature gases like oxygen, methane, or water vapor. In the broader context, microlensing serves as an invaluable addition to the exoplanet hunting toolkit. Each detection method, whether it be radial velocity, transits, direct imaging, or microlensing, contributes unique information about exoplanets. While transits and radial velocity are particularly effective for finding close-in planets, and direct imaging can capture detailed images of planets at wider orbits, microlensing fills the observational gap by detecting planets across all regions of their systems, regardless of distance from their stars. This comprehensive approach enables scientists to map out the full architecture of planetary systems and better understand the distribution of planets in different galactic environments. The impact of gravitational microlensing on our understanding of galactic evolution cannot be overstated. By cataloging planets in different regions of the Milky Way, including the galactic bulge, spiral arms, and halo, microlensing surveys have revealed that planets are not confined to any single region but are instead dispersed throughout the galaxy. This widespread distribution implies that planetary formation processes are universal, occurring across a variety of stellar and environmental conditions. As more data from microlensing surveys is collected and analyzed, astronomers can refine their models of galactic formation and evolution, identifying the factors that promote or inhibit planetary formation on a galactic scale. The implications of these discoveries extend to the study of dark matter as well. Since dark matter exerts gravitational forces but does not emit light, it is difficult to detect directly. However, microlensing events caused by dark matter objects, such as massive compact halo objects, MACHOs, have provided indirect evidence of dark matter's presence and distribution. By studying microlensing events in regions where dark matter is thought to be concentrated, astronomers can glean clues about its behavior and structure. This research holds the potential to solve one of the most enduring mysteries in astrophysics: the nature of dark matter and its role in the universe. Looking to the future, the combination of gravitational microlensing and next-generation telescopes heralds an era of unprecedented exploration and discovery. With projects like the Roman Telescope, the European Space Agency's Euclid mission, and potential collaborations with JWST, microlensing will likely uncover a vast population of exoplanets, ranging from Earth-sized planets in habitable zones to gas giants in distant orbits. These discoveries will not only expand our knowledge of exoplanet diversity, but also refine our understanding of planet formation, stability, and potential for life. As humanity ventures further into the cosmic unknown, gravitational microlensing stands as a reminder of the power of scientific ingenuity. By harnessing the natural lensing effects of gravity, we have transformed our view of the galaxy, discovering worlds hidden beyond the reach of light and unlocking the secrets of planetary abundance. Each microlensing event, though brief, contributes a vital piece to the puzzle, illuminating the grand narrative of our galaxy and offering glimpses of the countless worlds that populate it. In this journey of discovery, gravitational microlensing is more than a tool. It is a bridge connecting us to the distant reaches of the cosmos. It invites us to imagine worlds unseen, to ponder the forces that shape them, and to wonder about the possibility of life in places vastly different from our own. As we continue to peer through this cosmic lens, we may one day find that the mysteries it reveals are not just answers to scientific questions but also pathways to understanding our place in a universe teeming with unknown possibilities. Gravitational microlensing's unique ability to unveil distant and faint objects makes it a cornerstone of planetary discovery and galactic exploration. The scientific community's continued advancement in microlensing technology and methodology not only deepens our understanding of the Milky Way but also provides a template for exploring other galaxies. Although gravitational microlensing events are fleeting, capturing them consistently across wide areas of the sky could one day help astronomers detect planets around stars and neighboring galaxies. This would push our knowledge of planetary systems far beyond the bounds of the Milky Way, potentially leading to a more comprehensive grasp of universal planetary formation patterns and the cosmic forces governing them. The role of gravitational microlensing in galactic-scale observations is tied closely to the search for dark matter, one of the most profound mysteries in modern astrophysics. While dark matter does not emit, absorb, or reflect light, it is thought to comprise a significant portion of the universe's mass, influencing the gravitational behavior of galaxies and large-scale cosmic structures. Gravitational microlensing offers indirect yet valuable insight into the presence of dark matter, particularly in the form of machos or other compact objects that contribute to the unseen mass in our galaxy. By identifying microlensing events caused by objects lacking visible emission, astronomers can build a clearer picture of the dark matter distribution in the Milky Way and its role in the galactic structure. The potential discovery of exoplanets or planetary systems influenced by dark matter would open a groundbreaking new chapter in astrophysics. Such a finding could imply that dark matter affects not only the overall mass and structure of galaxies, but also the stability and dynamics of individual planetary systems. Observing gravitational microlensing events in regions dense with dark matter may reveal how gravitational forces are altered in such environments, potentially affecting how planets form and orbit within dark matter-rich zones. If exoplanets are confirmed to exist in these regions, it would suggest that planet formation is even more resilient and adaptable than previously imagined. As telescopes capable of microlensing observations improve, such as the upcoming ground-based Extremely Large Telescope (ELT) and 30-meter telescope (TMT), it is likely that new microlensing studies will capture planetary systems in even more detail. These advanced observatories will complement the data gathered from space-based instruments, like the Roman telescope, by enabling precise measurements of gravitational microlensing events. The combined efforts of ground and space telescopes will create a robust dataset, enhancing scientists' ability to study specific systems over time and trace the dynamic evolution of planetary orbits under the influence of galactic forces. In addition to dark matter, microlensing observations could potentially reveal more about the distribution of black holes within our galaxy. Black holes, like dark matter, are difficult to detect directly due to their non-luminous nature. However, they exert powerful gravitational forces that can produce microlensing effects. As a black hole passes between a distant star and Earth, it can cause a detectable distortion in the background starlight, enabling astronomers to estimate the black hole's mass and location. Observing such events would help chart the positions and prevalence of black holes throughout the galaxy, offering insights into their formation and the overall life cycle of stars in dense stellar environments. The scientific curiosity driving these investigations into planetary and cosmic mysteries is not just about cataloging objects. It is about pursuing answers to fundamental questions about the universe. What role do rogue planets, dark matter, and black holes play in shaping galaxies? How diverse are planetary systems across the cosmos, and could life exist in configurations that we have yet to imagine? Gravitational microlensing has become a tool that pushes the boundaries of what is possible in astronomy, continually revealing hidden aspects of the galaxy that challenge our assumptions and inspire new theories. In understanding gravitational microlensing's role in planetary science, it's important to appreciate the technological advancements and international collaborations that support these discoveries. Microlensing campaigns, such as the Optical Gravitational Lensing Experiment, OGLE, and the Microlensing Observations in Astrophysics, MOA, require substantial resources and teamwork from scientists and astronomers worldwide. OGLE, based in Chile, and MOA, operating from New Zealand, exemplify the global effort required to sustain microlensing studies, as they monitor millions of stars across different parts of the sky. Their shared data and cross-referenced findings ensure that microlensing events are identified accurately and quickly, maximizing the potential for exoplanet discovery and minimizing the possibility of missed events. The potential of these ground-based projects will be significantly amplified once the Roman telescope and other space-based observatories come online. While ground-based telescopes are subject to atmospheric limitations that can distort observations, the Roman telescope will observe from space, providing clear and uninterrupted data. This high-quality data will improve our understanding of microlensing signals, allowing astronomers to make more precise measurements of planetary mass, orbit, and distance. These enhanced observations will be critical for identifying faint, distant planets that remain out of reach for current ground-based efforts. The future of gravitational microlensing extends beyond exoplanet discovery into an era where the detection of habitable conditions on distant worlds becomes possible. While microlensing alone cannot directly confirm atmospheric composition, the technique can identify promising targets for follow-up study. Once an exoplanet is detected through microlensing, it can be observed later by instruments designed to analyze atmospheric signatures, such as the JWST. If signs of atmospheric gases associated with life, like methane or oxygen, are detected, it would suggest the tantalizing possibility of habitability, if not actual biological activity. In this sense, microlensing serves as a precursor, identifying planets that might be suitable candidates for detailed atmospheric analysis and, ultimately, the search for life. One particularly captivating aspect of gravitational microlensing is its ability to challenge our concept of habitability by detecting planets in environments once thought inhospitable to life. For example, planets in extremely wide orbits or rogue planets wandering through interstellar space are unlikely to receive substantial heat from nearby stars. However, if these planets possess subsurface oceans or geothermal activity, they could potentially harbor microbial life or other forms of extremophiles. Discovering planets with these unique characteristics could greatly expand our understanding of what constitutes a habitable environment, prompting a re-evaluation of life's potential to survive and thrive in diverse conditions. As the field of microlensing evolves, it also holds the promise of illuminating the distribution of planetary types within the galaxy. Some microlensing surveys have suggested that gas giants may be more common in the outer regions of planetary systems, while smaller, rocky planets could be prevalent closer to their stars. This distribution may reflect universal trends in planetary formation, hinting that similar configurations could be found in other galaxies. As we refine our techniques and gather more data, microlensing may ultimately reveal how common Earth-like planets are within the galaxy, offering clues about how typical our solar system might be in the context of the wider cosmos. The philosophical implications of gravitational microlensing are profound. Each discovery of a distant exoplanet reminds us that our place in the universe is just one among countless other possible realities. By studying planets in different regions of the galaxy, from densely populated stellar clusters to isolated rogue systems, microlensing confronts us with the extraordinary diversity of planetary environments and invites us to contemplate the likelihood of life elsewhere. The more we learn about these distant worlds, the more we are compelled to wonder if we might one day make contact with another form of intelligence or discover life in an unexpected place. This pursuit of knowledge through gravitational microlensing speaks to humanity's enduring curiosity and our drive to explore. By embracing the unknown and developing new techniques to investigate it, scientists continue to push the boundaries of what we can perceive and understand. Microlensing is a prime example of how creativity and scientific rigor combine to reveal the universe's hidden wonders, inspiring future generations to look beyond the immediate and imagine what lies beyond our current grasp. Ultimately, gravitational microlensing's contributions to science are a testament to the power of innovation in unraveling the mysteries of the cosmos. It is a field that exemplifies how a seemingly small or rare phenomenon, a brief distortion of starlight, can hold the keys to understanding planets, stars, and galaxies. With each new microlensing event, astronomers add a piece to the puzzle, constructing a clearer image of our galaxy and its innumerable worlds. Whether we are discovering new planets, exploring dark matter, or mapping black holes, gravitational microlensing allows us to transcend our earthly limitations and reach toward the infinite, deepening our connection to the universe. As the advancements in gravitational microlensing continue, the prospect of discovering even more elusive and distant planetary systems becomes increasingly tangible. The next frontier of this field lies in the refinement of observational techniques and the development of next-generation instruments that can capture microlensing events with even greater precision. These technologies will enable astronomers to detect planets not just within our immediate galactic neighborhood but across vast expanses of space, including regions that were once unreachable by conventional telescopes. In the coming years, we are likely to see an increasing number of collaborative international efforts aimed at harnessing the full potential of gravitational microlensing. A particularly exciting example of this collaboration is the ongoing work between space agencies such as NASA and the European Space Agency, ESA. These collaborations aim to pool resources, combining the power of space-based observatories like the Hubble Space Telescope and the Roman Telescope with ground-based observatories, thus creating a comprehensive observational network that can monitor vast portions of the sky simultaneously. By leveraging this synergy, astronomers can detect microlensing events with unparalleled accuracy, allowing for faster and more efficient discoveries. One of the more exciting outcomes of this collaboration is the potential to find planets in different stages of development, including protoplanets that are still in the process of formation. These young, developing worlds are extremely difficult to observe with traditional methods, as they are often hidden within the dense clouds of gas and dust that surround their host stars. Gravitational microlensing offers a unique way to peer into these distant nurseries of planetary systems, providing a glimpse into the processes that govern planetary formation across the universe. Understanding how these protoplanets evolve could help answer fundamental questions about how our own solar system came to be and whether there are universal patterns in planetary development. The ability to detect exoplanets around faint or distant stars, even those that might not be visible to traditional methods, also positions gravitational microlensing as a tool that could potentially detect planets in other galaxies. While detecting exoplanets within our own Milky Way remains a challenge due to the vast distances and the faintness of some of these planets, microlensing provides an opportunity to look beyond our galaxy. The discovery of exoplanets in other galaxies would be an extraordinary milestone in astronomy, not only proving that planets exist across the entire universe but also offering insights into the formation and evolution of planets in a broader cosmic context. In fact, there are already efforts underway to study the potential for detecting microlensing events in other galaxies. As technology improves, astronomers hope to use advanced space-based telescopes like the James Webb Space Telescope, JWST, to observe microlensing events not just in our galaxy but also in the nearby Andromeda Galaxy and beyond. The potential to detect exoplanets in galaxies outside the Milky Way would open up a whole new dimension of exoplanet research. These discoveries could radically alter our understanding of how planets are distributed across the universe, helping to answer some of the most profound questions about the nature of galaxies and planetary formation. The search for exoplanets via gravitational microlensing is not just a quest for new worlds, but also a search for knowledge about the types of environments in which life might emerge. As scientists identify and study planets that fall within the habitable zones of their stars, they are not just looking for planets with the right conditions for life as we know it. They are also expanding the concept of what makes a planet suitable for life. Could life exist on planets that are orbiting stars that are not ideal by human standards? Can planets in extreme environments, such as those with rogue orbits, or those located in dense dark matter regions, host forms of life that defy our current understanding? Gravitational microlensing is pushing the boundaries of habitability, challenging scientists to rethink what it means to live on a planet, while simultaneously paving the way for discoveries that could ultimately answer one of the most profound questions humanity has ever asked: are we alone in the universe? As we look to the future, the next wave of discoveries made possible by gravitational microlensing is sure to captivate the imagination of both scientists and the general public. The hunt for exoplanets is not only a scientific endeavor but also a philosophical one. As we uncover more planets orbiting distant stars, we are faced with the realization that the universe is far more populous than we once thought. Whether we ever find signs of life elsewhere or not, the mere fact that there are countless worlds out there, some similar to our own, others vastly different, expands our understanding of our place in the cosmos. In many ways, gravitational microlensing embodies the spirit of exploration. It is a tool that allows us to peer into the hidden corners of the universe, shedding light on regions that would otherwise remain invisible. Each new microlensing event brings with it the potential to uncover the secrets of distant planets, stars, and galaxies, deepening our understanding of the forces that shape the cosmos. Through these discoveries, we are not just learning about exoplanets, we are learning about ourselves, our world, and our place in the vast, mysterious universe. The future of gravitational microlensing and its role in exoplanet discovery is not just about technological advancements. It is also about inspiring the next generation of astronomers, engineers, and scientists. With each new discovery, we are reminded that the universe is full of mysteries, waiting to be uncovered. And as our technology improves and our knowledge deepens, the mysteries of the universe will continue to unfold before us, challenging our perceptions and expanding the boundaries of human understanding. From discovering new planets to investigating the dark matter that surrounds us, gravitational microlensing is a key tool in our quest to unravel the deepest mysteries of space. By combining the brilliance of scientific innovation with the curiosity that drives us to explore the unknown, we are slowly piecing together a picture of the universe that is as awe-inspiring as it is humbling. Gravitational microlensing has proven to be a valuable ally in this journey, and its role in planetary science is only just beginning to be fully realized. As we continue to explore, discover, and question, we are reminded that there is always more to learn, and the universe has far more to reveal. As we continue to push the boundaries of gravitational microlensing in the search for exoplanets, we are also advancing our understanding of the nature of these distant worlds. With every new discovery, we gain insights not only into the conditions on other planets, but also into the broader dynamics of planetary systems. One of the most intriguing aspects of this search is how gravitational microlensing has begun to challenge some of the conventional assumptions about the distribution and characteristics of exoplanets. One of the biggest surprises has been the discovery of a high number of planets that exist far from their parent stars, planets in what would be considered extreme, cold orbits. These exoplanets challenge the traditional idea of the habitable zone, the region around a star where conditions might be right for liquid water to exist. Gravitational microlensing has enabled the detection of planets that might not even be detectable using the standard methods, such as transit photometry or radial velocity measurements. These planets, often located in the outer reaches of their star systems, could still harbor the potential for life, albeit life in forms and environments we cannot yet imagine. Moreover, the ability of gravitational microlensing to detect planets in very distant orbits may also have profound implications for the study of rogue planets, planets that don't orbit stars at all. Rogue planets, which have been ejected from their original solar systems, are incredibly difficult to detect because they do not emit their own light and are often too faint to be seen by traditional means. However, gravitational microlensing can provide a way to detect these wandering planets by observing the temporary lensing effect they produce as they pass in front of more distant background stars. The discovery of rogue planets could shed light on the dynamics of star systems and the violent events that can cause planets to be flung into interstellar space. These findings could lead to new theories about planetary migration, the forces that shape planetary systems, and the potential for life on planets that are not tied to any particular star. In addition to expanding our understanding of the range of exoplanet types, gravitational microlensing also holds promise for discovering planets in other galaxies. The technique's ability to detect planets around faint, distant stars could allow astronomers to study exoplanetary systems that are located far beyond the reach of current observational methods. This could potentially lead to the detection of exoplanets in galaxies millions, if not billions, of light-years away from us, offering a glimpse into the diversity of planetary systems that exist throughout the universe. As we detect more and more exoplanets in other galaxies, we may begin to form a more comprehensive picture of how planetary systems evolve and whether there are common patterns across different galaxies. This potential to study exoplanets in other galaxies could also have important implications for the study of galactic evolution. By observing the types of planets that exist in distant galaxies, we may gain valuable insights into how galaxies themselves evolve over time, and what role planetary systems play in this process. The discovery of planets in other galaxies could help us understand whether planetary systems are a common feature of galaxy formation, or whether they are more of a rarity, shaped by unique conditions in certain galaxies. This could further challenge our ideas of what constitutes a typical galaxy and provide more context for the role that planetary systems, and possibly life, play in the evolution of the universe. One of the most fascinating aspects of gravitational microlensing is its ability to provide a snapshot of distant exoplanets that would otherwise remain invisible to us. Unlike other techniques that require continuous observation or the ability to track a planet's orbit over time, gravitational microlensing events can provide a fleeting glimpse into the presence of an exoplanet, with only a brief observation. This momentary view, however, can be incredibly valuable. By capturing the light curves created by microlensing events, astronomers can gather critical data on the mass, size, and location of the planet, as well as other important characteristics such as the presence of moons or rings. As more and more microlensing events are captured and analyzed, astronomers are building a more detailed catalog of exoplanets, which is beginning to reveal patterns in planetary characteristics across different types of stars. For example, some studies suggest that exoplanets found through microlensing are more likely to be gas giants, which is different from what is typically found using other methods, where rocky planets in the habitable zone are more commonly detected. This difference could provide important clues about the factors that influence the formation of planetary systems. For example, gas giants may be more common around older stars, or certain types of stellar environments might be more conducive to the formation of larger planets. These findings could eventually lead to a more nuanced understanding of how planets form and evolve. Gravitational microlensing also offers the possibility of discovering planets that might have been missed by other methods due to the limitations of detection techniques. For instance, planets that are too small to cause detectable dips in their host stars' light curves may go unnoticed using the transit method. Similarly, planets that are located far from their stars, where the radial velocity effect is weaker, might not be detectable by Doppler surveys. However, microlensing can reveal these faint or distant worlds by observing the subtle bending of light caused by their gravitational influence. This opens up a new realm of planetary discovery, where even the smallest or most distant exoplanets can be detected with the right observational tools. In the years ahead, the continued refinement of gravitational microlensing techniques will likely uncover many more unexpected and exciting discoveries. Advances in computational modeling, better image resolution, and the ability to observe microlensing events in real time are all likely to improve our ability to detect and study exoplanets. With missions such as the Nancy Grace Roman Space Telescope, which is set to launch in the near future, astronomers will be able to observe a large portion of the sky continuously, significantly increasing the number of microlensing events detected. One of the most exciting prospects of these advancements is the possibility of identifying planets that could be similar to Earth in terms of their size, location, and conditions. While the search for Earth-like exoplanets has largely focused on detecting planets within the habitable zone of stars, gravitational microlensing could reveal additional candidates that fall outside the conventional habitable zone, but may still be capable of supporting life in unique ways. These discoveries could expand our understanding of what makes a planet suitable for life and, in turn, help inform the search for life beyond our solar system. Gravitational microlensing has become an indispensable tool in the search for exoplanets, offering unique insights into some of the most distant and faintest worlds in the universe. As this technique continues to evolve, it will undoubtedly play a pivotal role in our quest to understand the diversity of planets that exist throughout the cosmos. By uncovering new planetary systems, exploring the possibility of life in distant environments, and advancing our understanding of how planets form and evolve, gravitational microlensing is helping to push the frontiers of planetary science. It is a powerful reminder that the universe is full of mysteries yet to be uncovered, and with every new discovery, we come closer to answering some of the most profound questions about our place in the cosmos. As we continue to explore the vast expanse of space through the lens of gravitational microlensing, we are not only refining our understanding of distant exoplanets, but also deepening our knowledge of the universe as a whole. One of the more profound implications of these discoveries is the potential for expanding our concept of habitable worlds. While much of the search for life has been focused on planets that orbit within the so-called habitable zone, the region around a star where conditions may allow for liquid water, gravitational microlensing has shown that planets with the potential for life might not be confined to these traditional boundaries. The search for exoplanets that could harbor life is one of the most exciting scientific endeavors of our time, and gravitational microlensing has played an essential role in this pursuit. By revealing planets that are located far from their parent stars, scientists are beginning to realize that life might be able to thrive in environments that were previously considered inhospitable. For instance, gas giants that orbit far away from their stars may not only offer clues about planetary formation but also present potential environments where life could exist in ways we have yet to imagine. But gravitational microlensing does more than just detect distant planets. It also provides critical data that helps astronomers better understand the atmospheres and compositions of these exoplanets. By measuring how light from distant stars is bent and focused by a planet's gravity, researchers can glean information about the planet's mass, size, and atmospheric properties. This information is crucial for understanding whether an exoplanet could have conditions suitable for life. For example, the detection of water vapor in an exoplanet's atmosphere could be an important clue in determining whether the planet might have the right conditions for life as we know it. As more and more microlensing events are captured, scientists are also learning about the distribution of planets in different regions of their stellar systems. Some of the most fascinating discoveries are those that challenge our preconceived notions about where planets should be found. For example, gravitational microlensing has revealed the existence of planets that are located in orbits far beyond what we typically consider the habitable zone. These discoveries expand the possibilities for where life might exist, providing a more comprehensive picture of planetary systems across the universe. One area where gravitational microlensing is likely to have a profound impact is in our understanding of rogue planets. Rogue planets are those that have been ejected from their parent stars and now travel through space without a fixed orbit. These planets are incredibly difficult to detect because they do not emit light and are often too faint to be observed using traditional methods. However, gravitational microlensing allows astronomers to detect rogue planets by observing the way their gravity bends the light of distant stars. These rogue worlds, often thought to be rare, may be more common than previously believed. The ability to detect them could change our understanding of the formation and dynamics of planetary systems, as well as the potential for life on planets that are not tied to any particular star. In addition to detecting exoplanets and rogue worlds, gravitational microlensing could also help us investigate the existence of other strange and exotic objects in space. For instance, microlensing could be used to detect brown dwarfs, objects that are too small to be classified as stars but too large to be considered planets. Brown dwarfs are often difficult to observe because they do not emit significant amounts of light, but their gravitational influence can be detected through microlensing. These objects, which are sometimes referred to as failed stars, may offer insights into the processes that occur during the early stages of star formation and could play a role in the evolution of planetary systems. The potential for discovering exotic and previously unknown objects in space through gravitational microlensing is immense. As new techniques and technologies are developed, we are likely to uncover even more fascinating insights about the nature of the universe. The advent of future space telescopes, such as the James Webb Space Telescope, combined with the ability to continuously monitor large portions of the sky, will further enhance our ability to detect and study microlensing events. This will allow us to uncover even more exoplanets, rogue planets, and other strange phenomena, advancing our understanding of the cosmos and our place within it. One of the most exciting aspects of gravitational microlensing is the way it complements other methods of exoplanet detection. Traditional techniques, such as the transit method or radial velocity measurements, have provided us with a wealth of information about exoplanets in nearby systems. However, these methods have limitations, such as their inability to detect planets that are too small, too distant, or too faint. Gravitational microlensing, on the other hand, can detect planets across vast distances and reveal objects that would otherwise remain hidden from view. By combining microlensing with other detection techniques, astronomers are able to create a more complete and accurate catalog of exoplanets, offering a clearer picture of the diversity of worlds that exist in our galaxy. The discoveries made through gravitational microlensing also have the potential to reshape our understanding of the history of the universe. For example, The study of microlensing events can help us investigate the formation and evolution of galaxies. By observing how light from distant stars is bent by the gravitational influence of intervening objects, whether they are planets, stars, or entire galaxies, astronomers can gain valuable insights into the distribution of matter in the universe. These observations could reveal new information about the distribution of dark matter, the expansion of the universe, and the formation of large-scale cosmic structures. Looking forward, the continued advancement of gravitational microlensing could lead to even more groundbreaking discoveries. As technology improves and our ability to observe the universe becomes more sophisticated, the potential for detecting exoplanets and other exotic objects will increase. The combination of new observational techniques, powerful space telescopes, and enhanced computational methods will open new frontiers in the study of exoplanets and the search for life beyond Earth. Gravitational microlensing has revolutionized our ability to detect exoplanets, offering a window into the farthest reaches of the universe. By providing a unique and powerful tool for discovering distant, faint, and rogue planets, this technique has expanded the boundaries of planetary science and opened up new possibilities for the study of exoplanetary systems. As our understanding of gravitational microlensing continues to evolve, it promises to uncover even more fascinating mysteries about the nature of the universe and the potential for life on distant worlds. The search for exoplanets, fueled by this innovative technique, is one of the most exciting scientific endeavors of our time, and its impact will continue to shape our understanding of the cosmos for years to come. As we continue our exploration of gravitational microlensing and its role in the search for exoplanets, it's essential to consider how this technique has already changed the way we approach the study of distant worlds. It has allowed us to peer into regions of the cosmos that were once inaccessible, revealing planets and planetary systems that are both familiar and strange in their nature. But perhaps more excitingly, gravitational microlensing has also brought to light the vast unknowns that remain to be uncovered. The full extent of the universe's potential for hosting planets, particularly those that may harbor life, has yet to be revealed, and microlensing could be the key to uncovering some of the most profound discoveries yet to come. One of the most compelling aspects of gravitational microlensing is its ability to detect planets that are orbiting in extreme conditions, far away from their stars. While the majority of exoplanet discoveries have been made around stars similar to our Sun, microlensing has been instrumental in identifying planets orbiting dimmer stars, as well as rogue planets that do not have a fixed orbit. These findings suggest that planets may be far more ubiquitous in the universe than we once thought, existing in places where traditional methods of detection would have missed them. These rogue planets, for instance, could be floating freely in the interstellar medium, far from the heat and light of any star, yet still potentially possessing the ingredients necessary for life. The role of gravitational microlensing in the detection of rogue planets is particularly intriguing. These planets, which have been ejected from their parent systems, are incredibly difficult to detect through conventional methods because they do not emit light and are often too faint to be observed using traditional telescopes. Gravitational microlensing, however, allows us to detect the gravitational influence of these planets as they pass in front of background stars. When a rogue planet crosses the line of sight to a distant star, its gravity bends and amplifies the star's light, producing a characteristic microlensing event. This event provides astronomers with the unique opportunity to detect the rogue planet's presence, even if it is located far away and emitting no light of its own. While rogue planets have long been thought to be rare, recent discoveries suggest that they may be more common than we once imagined. This realization has far-reaching implications, not just for our understanding of planetary formation but for the search for life in the universe. If rogue planets are indeed abundant, it's possible that some of them may have atmospheres capable of supporting life. Even in the absence of a nearby star, these planets could have geothermal heat sources, such as volcanic activity or radioactive decay, that might create habitable conditions. Gravitational microlensing has opened the door to exploring these distant, mysterious worlds, giving scientists new avenues to investigate the possibility of life beyond Earth. But the discoveries don't stop with rogue planets. Gravitational microlensing has also been instrumental in detecting planets that are located in the outer reaches of their stellar systems, far beyond the traditional habitable zone. For a long time, the habitable zone was thought to be the primary location where planets capable of supporting life could be found. This zone, often referred to as the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist. However, gravitational microlensing has revealed that planets with potential for life may exist outside of these traditional boundaries, particularly in the outer regions of their systems. These discoveries challenge our understanding of where life might exist, suggesting that conditions for habitability could be more flexible and varied than previously believed. One such example is the discovery of a planet in the far outer regions of its star's gravitational influence, which was detected using microlensing. This planet, located far from its star, may not have the warmth we typically associate with life-supporting planets, but it could have geothermal energy sources or subsurface oceans that allow life to flourish in unexpected ways. Microlensing offers the potential to uncover more of these outliers, expanding our understanding of the environments where life might exist. In addition to revealing distant planets, gravitational microlensing has provided scientists with a wealth of data about the mass and composition of exoplanets. When light from a distant star is bent by the gravitational field of a planet, it's not just the light's path that changes. The way the light is distorted can also tell us important information about the planet's size, mass, and even its atmospheric composition. For example, by studying the way the light from a background star is magnified, astronomers can infer whether a planet is a gas giant or a rocky world, and they can even learn about the presence of water vapor or other molecules in the planet's atmosphere. This ability to study exoplanets in such detail, even from light years away, is a powerful tool for advancing our understanding of planetary science. The method's ability to detect planets in distant and faint regions of the universe is a game-changer in the search for exoplanets. Traditional techniques, such as the radial velocity method or the transit method, rely on detecting signals from exoplanets that are relatively close to their stars or in orbits that are aligned in such a way that their movements are detectable from Earth. Gravitational microlensing, however, works by observing the way a planet's gravity bends the light from a distant star. This means that planets in distant orbits, even those far beyond the reach of traditional detection methods, can still be detected. The potential to detect planets in these far-off systems is particularly important as we continue our search for Earth-like planets that could potentially support life. By uncovering planets that orbit stars outside of the conventional habitable zone or in systems that are located in the far reaches of the galaxy, gravitational microlensing could provide the key to unlocking new frontiers in the search for life beyond Earth. These findings could challenge our assumptions about what makes a planet habitable and provide us with new insights into the conditions that are necessary for life to thrive. But gravitational microlensing's contributions to the search for exoplanets are not limited to the discovery of new planets. It is also playing a pivotal role in refining our models of planetary formation and evolution. By observing the way light is bent by the gravitational influence of exoplanets, scientists can learn more about the processes that govern the formation of planetary systems. For example, the size and distribution of planets in different regions of their systems can reveal important clues about how these planets formed and how their environments have evolved over time. The ability to study these systems in such detail will help astronomers build more accurate models of how planetary systems develop and how planets themselves evolve over billions of years. Moreover, gravitational microlensing can shed light on some of the most fundamental questions in astrophysics, such as the nature of dark matter. The study of microlensing events is helping scientists probe the distribution of dark matter in the universe by observing how light from distant stars is distorted by invisible objects, including dark matter. These observations could lead to a deeper understanding of one of the most enigmatic substances in the universe, which is thought to make up around 85% of the universe's total mass, but has never been directly observed. The combination of microlensing with other detection methods is poised to lead to even more exciting discoveries. As we continue to refine our understanding of exoplanet detection techniques and improve the technologies that allow us to observe distant stars and planets, we can expect the pace of discovery to accelerate. Space telescopes like the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and upcoming missions like the Wide Field Infrared Survey Telescope will provide unprecedented capabilities for studying microlensing events and detecting exoplanets. These missions will allow scientists to probe even deeper into the cosmos, revealing planets that are farther away and more difficult to detect than ever before. As we look ahead, the role of gravitational microlensing in the search for exoplanets will only continue to grow. This technique has already provided us with valuable insights into the nature of planets and planetary systems, and it has the potential to transform our understanding of the universe in profound ways. As our technology improves and our observational capabilities expand, the discoveries made through microlensing will continue to push the boundaries of what we know, offering us a glimpse into the mysteries of the cosmos that have long been hidden from view. The search for exoplanets and the study of distant worlds is one of the most exciting frontiers of modern science. Through gravitational microlensing, we are gaining the ability to detect planets that would otherwise remain invisible, revealing new possibilities for the existence of life beyond Earth. With each new discovery, we are not only learning more about the universe around us but also inching closer to answering some of humanity's oldest questions. Are we alone in the cosmos? What other worlds exist out there, waiting to be discovered? And what does the future hold as we continue our journey to explore the stars? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.